Should we start? Yeah. Okay, so they're coming. Yeah. Okay, so good afternoon and welcome to lecture 6. Of course, today we're going to see this guidelines for reporting statistics in publication. Mostly I will be focusing on Nature group and the Lancet and New England Journal of Medicine. Okay, so I know it is very clumsy, but these are the articles, the best articles that you can find in the literatures, focusing on the statistical guidelines and statistical methods that one should consider before publishing papers in a good reputed journals, right? So the most important is Nature itself, Nature methods. So they have their statistics for Biologist, which is similar to our lecture series. So they every month in the issue they publish one particular kind of a guidelines on one particular topic related to statistics, right? As you can see at the point of significance it says, and it has many different categories, right? So they have been publishing from past a couple of years. So I think it's a good starting point. So most of our lecture was basically motivated from that one. Then another Nature paper that was published actually in 2012, it was a call for transparent reporting to optimize the predictive value of preclinical research. This is very important and it's very eye-opening, eye-opener for the researchers, because they have highlighted so many issues which we, sometimes we just neglect, right, by publishing. And there are some couple of articles which are important. There is, by the way, there is also a consortium. So there is a consolidated, standard of randomized controlled trial. So there is basically a consortium on if you're doing a randomized controlled trial. Of course, we are not doing that one, but actually we can get a lot of inference from them, right? So there are some guidelines in order to how to publish papers considering the standard statistical methods. Okay, so focusing on this particular paper which I was mentioning, it is really surprising their results. The review was this one. So they reviewed the 100 articles published in Cancer Research in 2010, and they revealed that only 28% of the papers reported that the animals were randomly allocated. Only 28%. And then just 2% papers reported that the observer were blinded to the treatment. So basically 98% was unblinded. Yeah? And this is the highlight, that none stated that the methods used to determine the number of animals. So basically, nobody has estimated the sample size a priori. And that is basically the Cancer Research, right? So basically, it's very likely that it's going to use it for lead optimization in the phase 1 trial and phase 2 trial. So if you go to this Nature publication, and there is a link in this, my PDF, right, and leaflet. So these are the points in the Nature publication group, and I also included some points from New England Journal of Medicine and Lancet also. But no matter which journal you see, almost they are all the same, right? And they all focuses on these particular issues. Everything boils down to these many issues. So that's like sample size estimation, randomization, blinding, replication, descriptive statistic representation, how you describe different plots, and the correct statistical test, whether or not you have taken consideration of the assumption and whether or not the test is suitable for that particular analysis kind of thing. And the data handling, like for example, inclusion, exclusion criteria, or how did you consider the outlier, right? What was your definition of outlier? So these are all this issue. And what they want is, while you submit a paper, that they want that you should take care of that. Yeah, and also you should mention in the procedural methods. Because whenever you submit papers into all these journals, they will ask you the paragraph number and the line number and all those things, where it is mentioned. Right. So this is the text from the Nature statistical checklist for the sample size. And we do not have time to go through each and every statement, but if no sample size calculation was performed, the author should report why they think the sample size is adequate to measure their effect size. And of course, one can always say that this is the basic research and this is just the proof of concept, the pilot study and things like that. But if you really want to, think about the futuristic way, one should always consider the sample size estimation, a priori. That is always a good practice. So let's focus on the sample size. And we have seen in lecture 2 also the sample size dilemma. So if you have a too large sample size, it's a waste of time, like an animal and resources. If you have a too small, then less likely that to find a result. So the whole experiment itself is a waste, right? So there is no point in doing that. But if you have an optimal size, then there is a highly likely that you're going to find the effect size. We have seen what is effect size. It's a minimum detectable difference, what your research want, right? That's the effect size. Then you will find it. If there is that effect is there, then within that particular calculation, optimal sample size, you will find that for sure, according to the theory of estimation of sample size. Yeah. So if you see the sample size, there are two different scenario where you have to consider the sample size. One is the quality assurance and another one is group comparison. The quality assurance we have seen in lecture 1. We have actually derived this formula in lecture 1, right? So the sample size, so if you have just one group and if you just want to know that what should be my sample size in order to have the quality, the best quality for that particular group, let's say for the control, if you're just thinking about how many cells should be there, how many wells should I scan or stain, right, in order to have just the control population, then this is the quality assurance. We're going to see the example, right? So what is this sigma? Sigma is the standard deviation and WC as the width of confidence interval, right? Well, the group comparison, this is very important. This is, I think, most of the reviewer ask for this one because we always compare with the control, right? At least we have more than one control, one group. So this depends on this Z alpha by 2, and that is beta. So that's a type 1 error, type 2 error, standard deviation for the group 1 and group 2. And this delta is nothing but the effect size. So sample size depends on the effect size. How much difference do you want to study in your experiment? And also the alpha and beta and standard deviation. We're going to see this. And I have also shown in lecture 2 the demonstration of this software, how to calculate this. We do not have a time, unfortunately, today. So let's take this example of quality assurance, right? So quality assurance for the, let's say, animal example, that find the sample size in the control group for the antihypertensive herbal drug. I'm just going it rapidly because we have seen this example in lecture 1. So researchers want to set the width of confidence interval to plus minus 20 millimeter of mercury, and suppose the standard deviation, the previously conducted study was 25, and the level of confidence was 95%. You just plug in this values into this formula, and you get 6. So 6 rats should be considered in order to have such thing. Because if you do not do this, then you cannot expect that the confidence interval that might go from anywhere, right? So in order to assure the quality that your confidence interval will not vary from plus to minus or minus to plus 20 milligram, because please note that we are not considering any mean value here because we don't know what is mean value. Because to get the mean value, we have to conduct an experiment. But you might argue that how can I get this value without doing an experiment? But this value, you can get it from previously published your collaborators or whoever is working in your domain. You can get some ideas, or you can do some pilot experiment in order to get this value, right? And you just plug in this formula and then you get the sample size. Then you are assured that the quality is there, right, with this one. Let's take an example of a high content screening. I think we have also taken this example. So find the sample size number of wells to be considered for the control group to study the DNA damage, which is the gamma H2X, right? So researchers want to set a width of the confidence interval of plus minus 10 gamma H2X in this intensity, DNA intensity range, and the standard deviation is 300 units, right? So you just plug into this formula, you get the 3, 4, 5, 8 cells. And if for the 10x objectives, then roughly 500 cells per field. So number of fields would be 7. To be conservative, let's took it as 8. Then it becomes 4 wells with 2 fields per well. So that's basically sample size one should consider for the quality assurance. Yeah. Yes. I'm going to come to that. The discrimination is basically based on one group versus another, right? Yeah, that's what. So that's the next slide. So this is all about the quality assurance, meaning that when you have just one group, right? So it's very unlikely you're going to use it. But the reason why I put it is because I have collected all the literatures from the sample size issue, right? Nobody, I mean, very few people have mentioned about the quality assurance using the sample size. This is where your answer would be. So sample size consideration for group comparison, right? So when you want to compare between the two groups, then you need to know this one. And we have seen this in lecture 2 also. But there will be always an unknown truth. That is your null hypothesis. It will be true and false, two conditions possible. And what you observe can also be possible with a H0. Either you accept null hypothesis or you reject null hypothesis, meaning that no difference observed, there is a difference, right? So you accept H0 when actually H0 is true. That is called as a correct decision. That is basically true negative, right? Similarly, we can have a correct decision as true positive because you reject H0 when H0 is false. That's true. What you cannot make a mistake is this one. That is called as a type 1 error. That's called as a false positive. You reject H0 when actually H0 is true. You shouldn't have done this, but because of your observation, you reject H0 when in reality H0 is true. Similarly, you have a type 2 error. That is a false negative. That you accept H0 when there is there is a difference, right? H0 is false. And this is called as alpha, that is a type 1 error, and this is beta, that's called a type 2 error, okay? So alpha is also called as a probability of making type 1 error. That's a false positive. And is also called as a level of significance. So reviewer will always ask you what was your level of significance during your test, whatever test you have used, right? So you have to use that alpha value. What is beta? Beta is a probability of making type 2 error. And this is the interesting part. So 1 minus beta is nothing but the power of your test. And this is very, very important. And I'm going to show you the graph, why it is important. Okay, but let's talk about more about this alpha. We have seen this in lecture 2 actually, but let's repeat that. So what is the clinical definition? The chance of conducting that the experimental intervention is more effective than the control when in reality it is not. So what you're doing is that because of your observation, there is something gone wrong, and it is showing a difference. In reality, there is no difference. So basically, technically, it is that rejecting H0 when H0 is true. And this is very important for the reviewer. That's why a reviewer will not compromise to further increase this error. That's why always, whatever the p-value in statistics use, the level of significance is 5%. You cannot go beyond that. Because if you go beyond that, then you can always show some difference when there is no actual difference, right? That's why they don't want to compromise on this issue. That's why it is important for the reviewer or for the FDA or for EMA or whatever, right? And most commonly used is 5%, as I said, with the two-sided. We're going to see that what is this two-sided thing. And low alpha is good, of course. Yeah? What is beta? Beta is the chance of concluding that the experimental intervention is not more effective than the control when the reality is set. So that's basically reverse of the other one, right? And here it is important that the technical definition would be not rejecting H0 when H0 is false. And the power is nothing but the 1 minus beta, right? So the probability of rejecting H0 when H0 is false. Yeah? So this is basically, with your observation, you are showing that there is no difference. And actually, there is a difference. And this is very important for me or for anyone who is doing experiment, right? Because our whole aim of publishing paper is to show that my intervention is better than something else or control position. But if you do not take care of, if the beta is, if the beta is high, this error is high, then you're not going to show the difference. Yeah? So that's why the probability of rejecting H0 when H0 is false, that is the power basically. So power has to be high so that the type 2 error will be less. Okay? So that is important for pharmaceutical industry, yeah, and the researchers. And most commonly used power is a 0.6. That is a very minimum, right? One should not use that. Always, reviewer will ask you to have the power 0.8 to 0.95, which again depends on what kind of research you do, right? And I'm going to come to that one. I can see your smile. So, so low beta is good, high power is good. That is for sure, right? And this is just the equation that we have seen. So you don't have to worry about all these values, right? There is a software, and that software you just plug in play, and you can just get the power, right, and sample size. And I'm going to show you. So this is how the software will look like. And software has an option about what kind of a test family that you want to test your hypothesis on, right? So if my interest is to find the mean difference of the mean between the two groups, then of course we have seen that, we have stated that we have to use t-test, right? That's a t family. I have to select here the mean difference. And what I have to do is just I have to only put the mean value for group 1, which is 12 here, standard deviation of the group 1. Similarly, the mean of group 2 and the standard deviation of group 2. Just put that value. You hit the calculate button. The software will calculate the effect size for you, because effect size, that's your answer, by the way, you asked that day. So that's the effect size. And effect size, there are so many options for the effect size. So one can go for the Cohen's d. That is the simplest effect size calculation based on mean and standard deviation, right? But the point is that it calculates the effect size. You just place this value here. You choose what alpha you want, type 1 error, how much power do you want, and how you want to allocate the samples between the groups. 1:1, then it's an equal size. You just hit the button and then it will give you the answer, that is 4. So the sample size for the group 1 and sample size for group 2 has to be 4, 4. So there are total 8 samples needed for your experiment in order to have the power of 95% with the alpha 5% level of significance. Yeah? Now how it changes? Because you have, this is specific, this sample size is specific for this particular effect size. Now this graph will show you that x-axis is the power, y-axis is the sample size, and the slope, all these colors represent the effect size. And you can see that if the effect size is less, the sample size required for a particular power is more. And it increases from 0.6 to 0.95. And similarly, and when the effect size is more, you don't need much sample size, right? But the important point here is that if you have this plot, and if you're filing for funding or research grant, you can always argue and say that I'm focusing for this particular effect size for my research, and then you can say that I am looking for this particular power. If you give me the funding, I won't be able to achieve and allocate these many samples. I will be only having the 6 samples, and so that my power will be less. So don't expect result from this grant, kind of, yeah. But this is really good idea, and if it is a big grant, then I think you have to publish this plot, basically, yeah, so that you're sure before you start your experiment, right? Yes. The effect size is the difference between the mean of one group with respect to the mean of another group divided by the pooled standard deviation. And that is basically, you don't have to look into the formula because the software will calculate formula for yourself. Yeah? So this is basically that. What you need is just mean and standard deviation of 2 groups. That's it. Okay, so there is another issue with the sampling that is called as a bias, right? So the bias, there is a sampling bias, and that can be get rid of randomization. There is an experimental bias, so we can avoid that with a blinding. Design bias, we can take care of confounding factors so that we get rid of the design bias. Procedural bias, we need a technical replicates to get rid of that. And then we need a biological replicates to address this sample bias, the biological variations. And we're going to see that. So randomization, this is the text from the Nature Statistical Checklist. And what is the highlight here? The highlight is that randomly assigned to the experimental group may influence the experimental outcome. So basically, your outcome is influenced whether or not you do random sampling or random allotment to the samples, to the groups, basically. The statement about randomization method should be included in the experiment. This is very important, you see. So we have to explain somewhere. And for the in vitro experiment, absence of this statement is taken to mean that there is no randomization. So, yeah. But I would say if you're doing randomization in vitro, like for example, high content screening, if you're doing randomization post-processing, like for example, image analysis with the different plates and a blinding cross-validation, it is always a good idea to mention that you're doing that. You may not be doing in the bench side, but you're doing on a computer, kind of a cross-validation. So it's a good idea to say that. Example for randomization is, this is the example we have seen in lecture 2 about the randomized control trial. So you have a population, you have a cohort, you sample from there, which is the red and green here, and then you randomly allocate them to the treatment group and the placebo or control group. And there is an investigator which intervene the intervention, and then you follow them over time to see whom got the disease and whom doesn't get disease, right? What if we do not do this randomization? If you do not do this randomization, there is a likely that there is some predisposition because of some other factors, which you can see here, green and red. There are more greens and more red here. And that will affect your disease, the outcome. So your disease outcome is not basically controlled by whether or not your intervention works. So it is something else. So that's why the randomization is important for this one, right? Okay, in case of the high content screening, you can have the, in the left column you have a positive control, negative control. Either you can have a randomized, position of the wells. That is also good practice, but the point is the post-processing will be hard. So best way is the alternate columns with the positive and negative control. But if you have a big screening, you can't afford to have like this, right? So we have already discussed about if you cannot achieve this, but if you have some kind of age effect and all kind of effects, intervariability or intraplate or interplate variability, how to get rid of that by normalization. We have discussed that in lecture 4, so I discuss that now. The blinding, whenever possible, investigators should be unaware of the sample group. This is very important. So one should not be biased towards who is getting treatment or not. So we require a statement describing the level of blinding. Level of blinding, because there has to be the fold-wise blinding, right? How many people were involved in the blinding? Because there are so many stages during the experiment. So are they all blinded towards the experiment or not? That you have to mention that. So again, the same thing, the absence of the statement is taken to mean that there is no blinding, right? So if you do not mention, it means that we will say there is no blinding. Yes, so about the blinding thing, again, if this is an investigator, if he should be blinded, who is getting treatment and who is not getting treatment. That is the whole idea of blinding, basically. Confounding factors, we have seen this example as a case control study. So in the case control study, we have a population, we select samples, those who have got disease, those who do not got disease. And then we try to go backward in time, that is a retrospective study, case control study, to see which risk factors they were exposed to, so that you can correlate that risk factor to the disease, the cases, right? But in such cases, one should take care of the confounding factors. Confounding factors would be age, BMI, gender, which has nothing to do with the disease. Because if you do not take care of that, you might deceived by the result, right? That may not be directly proportional to the risk factors for the cases. So one should get rid of this confounding factors. And we have seen how to get rid of this confounding factors in linear modeling, right? We have seen in the previous lecture, the interaction, switch on the interaction and all this thing. So one can get rid of that also. So we can have a matching pair while developing the models, right? The replicates. It is often unclear whether replicates present biological or technical replicates. Even the nature accept that it is very confusing things. And I think I remember the youth and me, and I think all of us spend a lot of time on discussing what should be called as a technical or biological replicates. So if you see this, in reporting the result, authors should provide enough details about the sampling collection, how the sampling has been done, how sample collection, to distinguish between the independent data points and the technical replicates. So one should distinguish biological replicates and technical replicate as much as he can explain. The biological replicates are intended to reflect the biological variability. They are just explaining what is the biological replicates. And same thing here is also the technical replicate, that the author must specify the number of times this experiment was successfully repeated to know whether or not you have taken care of the technical replication. But let's see in detail what is technical and biological replicates. And we have seen this before. This is just a generic protocol. Okay, you might vary some boxes here depending on what kind of research you are doing. But you have a human or you have animal, you may be working on that. You collect the tissues, then you sample preparation, then you have an image acquisition, you have image analysis, you do data processing, and then data visualization, and then statistics and whatever, right? This is a common workflow of any experiment. But you have a variation in every stages, in every block set. And that variation in this case would be the variation in biology, this case, the variation in chemistry, from image acquisition to only this image acquisition, because that's the instrument, that's like a variation in physics, and variation in algorithm, like a computer science and all the algorithms that you write. So this is basically variation, and one should take care of that variation, right? That is nothing but basically having the technical and biological replicate. So to take care of the variation in biology, you have to have the biological replicates. To take care of the variation from chemistry to algorithm, you have to have the technical replicates. That's a procedural bias, and this is a sample bias. This is just a typical example I just collected from this source. So they have nicely explained that. Well, this is not my domain, but I'm trying my best to explain you how you should do, and I never did that. So you have a vial, right? You have a samples in the vial, and then you collect that samples in the culture dish, petri dish, right? And then you treat one petri dish with certain intervention, right? And then you collect samples on the glass slide. This is as bad as you can go, right? What he's saying is that one can improvise further, that you have one vial, but you can collect that vial and prepare samples, let the cells grow in a different petri dish, and then collect samples. Make sure that you're not improvising the sample size. Sample size is still same, but this is just the procedure, how you improvise your experiment. Again, this is a marginally good, right? But then if you want to improvise further, you can actually go from one day to another day. Repeat the same thing with one day to another day, so they will get rid of temperature and all environmental variations. If you want to further improvise it, then you can repeat this experiment for different cell lines. This is where you incorporate kind of the biological replication, because there's different biological. But if you think of singularity, there is a singularity concept in physics. Everything boils down to one, right? The black hole. Then nothing is biological replicates, right? But try your best to have this, taking care of the cell lines and the procedural bias. Okay. The descriptive statistics. This is where how you show the result, the plot, the graphs, things like that in your figure, the legend. So if I show you, and this is the most of the time any experiment does that, like you have a control group and you have many other groups which you want to compare with, right? And the y-axis is just the readout. This is just for the example. But if I show you this bar chart, or if I show this bar chart to the reviewer, and in the legend if I write this is the p-value and this is significant and all, this is not a good idea, right? In order to, if I just ask you, can you compare and can you say that the group 1 is significantly higher than the control? You cannot say. Or can you say? Can you say? You cannot say. Why can't you say? Just question. Because I can see that it is bigger than, or maybe I can say the group 3 is bigger than control. Why can't I say that it's a statistically significantly higher, the group 3, than the control? Exactly, that's right. So in order to, the bar chart is not sufficient. What we need is also the variation. And that is basically called as the error bar, right? And that error bar will be, the basic error bar to show is the standard deviation. So you just need a mean value, but you also need the standard deviation. That is the error bar, right? But this is just the minimal way. This is a very primitive way of showing the errors. One can improvise further, saying that, okay, I can show the standard error of mean, right? And we have seen in lecture 1, what is standard deviation? Standard deviation is the mean of all the deviation for every value from its mean. Average of all the deviations, right? But that is only for the one particular sample, standard deviation. While the standard error of mean we have seen, that is the standard deviation divided by under root of n. We have derived in lecture 1, right? That's the standard error of mean. What does it mean and why it is important? It tells you the standard deviation of the sampling distribution in this control. And you're always going to find this lower than this one. And this has been mentioned in all Lancet, New England Journal of Medicine, and Nature, that please do not show the standard error of mean for the samples. Because you're trying to show, I mean, not unknowingly, well, unknowingly, knowingly, but you're trying to show the reviewer that the variation in my sample is less, which is not true, because this is not the standard deviation, this is a standard error of mean. So make sure that what is your standard error of mean based on. So normally it is advisable to show standard error of mean for replicates. So if you have many replicates, show the standard error of mean for that. Okay? Also, otherwise, if you do not want to get rid of all these things, the best practice is to show the box plot. That is always the last resort. And I think I think it's from the last one decade basically, people have been, all the reviewers are asking basically to show not the bar chart but the box plot, so that with the box plot you can get all the information. You don't have to go through all this text in the legend and all. So the box plot is the best way to represent the data and data variation. So we have discussed box plot in lecture 3, right? So you see this is a rectangular box. The upper line indicates the third quartile. The lower one is the first quartile. The line, the thick line, the white line indicates the median value, while this dotted one indicates the average value. Okay, and this, the whiskers, they indicate the minimum value and the maximum value. Okay, and there is also the whiskers here that would indicate what is the outlier, what is the margin for the outlier, and that will be calculated as a 1.5 times the width of this box, which is nothing but the interquartile range. We have seen that Q3 minus Q1. That's from third quartile to first quartile. The difference times 1.5 times. Anything beyond and low considered as outlier. Yeah, but you have to explain that in the text or the procedures, that how you have because there are so many other techniques to define outliers. This is just the whiskers way of defining the outliers. Okay, but and then you can also show the confidence interval. This is the best part. You see, while here you can also replace this one with a confidence interval. That is also possible. But if you can show everything in one chart, why not use the box plot, right? And also the good part of the box plot is with the confidence interval, if I only show this plot to the reviewer or to myself, I won't be able to still get the p-value just by looking at this error bar and the mean value. Not with the standard deviation and not with the standard error of mean. But with the confidence interval, I am very confident that if the confidence interval are not overlapping, meaning that it has to be statistically significant, right? While the otherwise is not true. If the confidence intervals are only marginally overlapping, there may be a case that the p-value is marginally significant. But if they are not overlapping, means that it is for sure it is significant. It's very important. Okay. So I can say that because they are overlapping, so they cannot be statistically significant. But of course, this control and the group 3 has to be statistically significant. They're different, right? Because the confidence interval are not overlapping. Okay, on the top of this, if you just want to impress the reviewer, you can also show the box plot. On the top of it, you can also show the distributions. So he can just go through each and every data point. This is very good, actually. Of course, this is not possible for all the statistical toolboxes, but this is from the Spotfire, right? But this is really good, right? Because then you show him everything. The individual data points, median, mean, confidence interval, and everything, right? And you can also see that whether or not your distribution is Gaussian or not. This is also important. Want to test, and if you want to argue that you have used a parametric test or non-parametric test. Okay, but once you do that, you might also want to consider the multiple comparison. And this is what normally in all the papers, in the biological paper, I have seen that the horizontal line and the stars, right, to compare. And that is also called as a post-hoc analysis in like SPSS language. But there are different types by which you can achieve that, right? Because according to the theory, if you have more than 2 groups, and if you're just doing pairwise or unpaired t-test or whatever test multiple times, you are increasing type 1 error, okay? And you cannot report the individual p-values if you are doing that t-test multiple times, because you're lowering the power, right? And also you're increasing the type 1 error. So you cannot use 0.05 as your level of significance. You have to decrease that if you have multiple comparisons. So these are the techniques like honestly significant difference, least significant difference, Tukey-Kramer, Dunn-Sidek, Bonferroni, and Chaffee. So you can see that Bonferroni is the most famous doing this multiple comparison. So if you do not want to use this, we have seen that one can also get rid of this multiple comparison and one can just use ANOVA, one-way ANOVA. What ANOVA does is simultaneously it compares the groups simultaneously. But the problem with ANOVA is it only gives you one p-value. Well, it is good also because if your aim is just to find whether or not any one of these at least different from the others, then it's good. But if you want to compare one by one, then it's not good because it's just a p-value. So this is a p-value. Then we can do all these calculations depending on what algorithm you want to use for comparing. So you can see this the group 1 and group 2. So this is a comparison, the pairs basically. So there are 5 groups, so there can be 10 different possibilities of comparison. And this is the Tukey-Kramer. This is the p-value that you get. Bonferroni, Dunn-Sirak, LSD, Chaffee. Okay, so there are different variation, different calculation. There are different scenario, but it is okay as long as you're taking care of that. That's fine. You just have to mention in your text that how did you do the multiple comparison. Mostly, if you write Bonferroni, people would accept it because this has been used many times. But if you're doing some proteomics research, then I think this FDR is very famous. False detective rate, right? False discovery rate. That's a Benjamini and Hodgberg procedure. It is very handy. Actually, you don't need a computer. You multiply your p-value with a number of groups, that is 10. Just that would be your level of significance, and then you compare that, and then you multiply with the 10 to 9 when you sort the p-values. Okay. Yeah, the interpreting p-values. I think this is very important while writing also, while reviewing also the papers, right? So we have seen actually in lecture 3 what is p-value because there are so many definitions in the literatures, right? And he is the inventor of, he discovered the p-value, the way you compare the groups, Ronald Fisher. So what I like the definition about p-value is this one. The p-value is a probability of obtaining the value of the test statistics or more extreme just by chance alone when null hypothesis is true. I really like this. And I have explained what does it mean actually in the lecture, so I don't want to spend time on this because we don't have time. But what is important is the test statistics, and in layman's language, you just say that the false discovery, right? The probability of finding the false discovery. And of course, we don't want false discovery. We want a very less false discovery. So basically, p-value has to be as less as possible. That's called the false discovery, probability of getting false discovery in your experiment. Yeah? Okay. But just one example that what does this p-value means. So we have seen this example of student t-test, right? And then we have seen that there are different ways by which we can use t-test depending on what is my purpose of using. But no matter what you do, chi-square, z-test, t-test, Fisher test, you always collect the test statistics. And what you do is you plot your null hypothesis, you find a critical points, a critical line, and thereby you find a critical region based on level of significance. And with this, the test that you use, you just try to see if that test statistics is falling in a critical region or not. Okay? Because if they are falling in a critical region, you of course reject null hypothesis. But then what is the p-value? P-value is nothing but if this t is coming here, then whatever is in the right hand side will be the probability. That's the p-value basically. The area under the null hypothesis in the critical region. That's the p-value. Okay? Also, it is very important, and this is from the reviewer, that you should always mention whether or not you have used two-tailed or one-tailed test for any, whatever the test statistic that you're using. Because there is always a possibility of the left-handed, right-handed, and the both. So what does it mean? So if my null hypothesis is A and my condition is B, so I want to see if the B is different than A, then of course I'm going to have, so if I say, let's say I'm doing some experiment and I know a priori that B is always going to be higher than A. In that case, it is okay to use one-sided test. That is the left-handed test. In this case, left-handed, right? But if you're not sure, then you cannot use one-sided, because there is an advantage of using one-sided. Because the moment you use a two-sided, you compromise your power. And that is what the example here is. So that this is a one-sided, right? And the two-sided, this is my null hypothesis, right? A is my null hypothesis, and I'm just putting a critical line in the left-hand side and the right-hand side of the null. And I'm seeing if the B is different than A. But I'm checking in the both side, because I'm not sure whether B is going to be higher than A or it can be lower than A, right? So if I use only one-sided test, my test statistics and the p-value for the one-sided would be 0.04, which is less than 0.05. So I say, okay, I accepted. The test approved my result. But if you use a two-sided test, that has to be multiplied by 2, and that becomes 0.08, and that is no longer less than 0.05. And this is why reviewers will ask you to use two-sided test when you are not confirmed about this. And this is very, very critical when you have the effect size is very less, right? For the basic research, it doesn't matter. But if you do not show your result significantly different, then you lose your funding and whatever, all the consequences you have. So this is very important, especially for the non-inferiority trials. If you want to show that the drug is as good as the state of the art, then you should take care of the left-hand side also, because it should not show that it is worse than the present state of the art, right? And this is one example that we have seen, that this is just the one samples here. So it is a less, they are lower value, they are higher values. But if you go for the left and right, then you have a p-value. But if you only use for the left, the p-value is decreased further, you see? This is the effect of having only one-sided. So if you go further and further, this is not important, but we have seen the significance here, right? So if you use only one-sided test, it is likely that you're going to show the significant result. So it is important to mention you have used two-sided or one-sided. Correlation. So for correlation, we have seen this. First step for the correlation is always plot a scatter plot, so that you will come to know whether or not you have outliers in your data set. Okay? Second step is check if the plot is linear. Then only apply Pearson's. I have seen some papers, actually very nice papers. They blindly just apply Pearson's without even showing the scatter plot. And because nobody has asked whether or not you have checked the linearity, because if the relationship is not linear, one cannot apply Pearson's. So it is not blinded. It's just not like, it's not like a formula. You just put it. Of course, the equation will give you some value, but you have to see if it is a right way to do it, right? If you're not sure whether it's a linear or not, then you should see again if it is a monotonic. Monotonic meaning that it doesn't matter if it is like the curve-like structure. We have seen that actually, the curve-like plot, but as long as it is increasing or decreasing across the time or across the x-axis, that's fine. That's a monotonic, right? Then you can apply Spearman's rule. That is important. I have seen many papers saying that we have checked the normality, the data is not normal, that's why we use Spearman's. That is wrong. One should also check, because there is also assumption for Spearman's, that is the monotonicity. Because if it is a U-like or W-like structure, you cannot calculate Spearman's. Okay? And if you're not sure, then you're going to apply the Kendall's tau. But as you will see that the Kendall's is basically very fancy concordance and discordant joints pairs. It is a non-parametric, so of course you're going to lose your power. But of course, if there is no resort available, then that's the final resort, right? Important is always mention p-value besides correlation coefficient. I have also not seen this one, because I have seen only the scatter plot and then this line and then the R value. But it is very important whether or not that correlation is significant or not. It's very important. Of determination, the R square value, because that will tell you how much variation in X is explained by the Y. Because R can be very nice, right? Let's say 0.7 or something, but when you square it, it goes down less. And that is basically the reality of the association. That's why it says that the correlation coefficient has to be 0.7, so that at least you have a 50% of variation explained. Then to check the normality, right? We have seen this actually. There are so many tests, so one should use this test to check the normality conditions. And my favorite one is this Anderson-Darling test, but one can use the Shapiro-Wilk. That is the best option. I mean, most robust technique. Then we have a Kolmogorov-Smirnov and then the Lilliefors test. Just one example. So you have you have your sample, then you can always plot an histogram. But with the just by seeing the histogram, of course, for this case, I can say it is Gaussian, right? It looked like a bell-shaped curve. And of course, with the Anderson test, it says that it has been, it could have come from the normal distribution. But normally, when you do experiment, your sample size is less. So like 7 sample size. And then if you try to plot a histogram, just by looking at histogram, you cannot say it is normal. But here is a point. And I think the most of the user I have seen, they just look at the histogram and say, okay, my data is not normal, but that is wrong. That is not an assumption for the parametric test. The assumption is that whether or not this data has come from the normal distribution, that is the assumption. So if you use this test, the test will tell you that this could have come from normal distribution. So you can actually use t-test. Okay? So the criteria for using parametric test is not that the distribution has to be normal, but it has to come from the normal distribution. Okay? And then you can use this Lilliefors test, but there can be a situation, let's say Kolmogorov-Smirnov, that would reject your hypothesis. So of course, if you want more power, then Anderson-Darling, then the Lilliefors, and followed by Kolmogorov-Smirnov. Which test statistics to be used? You have to justify why did you choose that particular test, right? Because, and that can be decided and that can be answered to the reviewer that this was my purpose of hypothesis and this is my nature of my sample. That's why I have used this particular test. Then you don't have to answer that why did you use that particular test, right? If a priori, if you write in the text. So, and we have seen this actually, this chart from across all the lectures. So yeah, you have to just explain what is the purpose of your hypothesis and what is the nature of your sample. Yeah? If your sample is not Gaussianly distributed or it is not coming from the Gaussian distribution, then you have to use non-parametric test, and this is why I have used this test, right? But one should always avoid using non-parametric test because it will lower the power, right? And these are the further readings from the natures, but that is domain specific. So, and also I think this is what where I belong to, this microscopy guidelines, but this is for acquiring images and what is the quality of the image and all these things, but I think we should also go for that. Biomarker studies is also important, right? And we have covered this one, the animal preclinical studies, we have already covered this. That's the ARRIVE guidelines, all this randomization and the replication and things like that. Yes, and thank you so much. And we go into, so there is, now I can only have one lecture, okay? And because we didn't have, we couldn't take the previous lecture, so I can either go for lecture 7 or lecture 8, which is the hands-on activities. And lecture 7 has clustering and all the fancy and machine learning and the principal component analysis. So because I'm leaving, so I can only attend either of this lecture. And the rest of the lecture I can come and I can attend and give after I come back. That is on the 20th of November, right? So you tell me which lecture do you want me to organize next Monday out of these 2, so that we can, so I can prepare for that. If you're interested, of course. 7 would be nice. Okay. Yeah. 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 Okay. Good. Yeah. Good. Perfect. Okay. Then that's it. Thank you so much. No questions, right? Okay. Good. I'm going to send an email, yeah, about this. Yeah.